So in this video, we're going to be looking at how we can model pressure and temperature in relation to altitude for a given ideal gas or air. So we're going to start out with the basic equation for static fluids, dP over dz equals rho times A, which I already have up there. And another way we can write this is, and this assumes that z is positive and g, or acceleration due to gravity, is negative. Another way we can write this is pressure times the average molecular mass of our ideal gas divided by RT times minus G. And again, this is because we're assuming our Z direction is positive. So dP over dZ is equal to pressure times molecular mass over RT times negative G. We'll come back to this equation in a minute, but for now we're going to look at the change of internal energy of an ideal gas. So if we have some small energy Q that we're not going to worry about, minus P times the change in specific volume, we can rewrite this as CV delta T. It's going to be equal to negative, and since this is an ideal gas, we can rewrite pressure as negative RT over V dV. And then from here, we can divide across, and I'll move over here. We'll have CV dt over T equals negative R dV over V. That was the worst V ever written. And then from here, we can integrate both sides. So we're going to have, and we can take out CV because that's obviously going to be a constant. And in this scenario, we're going to be looking at a ideal gas where we know the specific volume and the temperature at a certain altitude. So in this case, we'll call that V1 and T1. We're going to be integrating up to some unknown temperature and some unknown specific volume. So we'll have dt over T, and then dV over V. Then after integrating, we'll have CV ln of, sorry, just making sure I didn't forget my negative sign on the other side, negative ln of T over T1, and then on the other side equals negative R ln V1 over V. Sorry, I got a little bit ahead of myself here. Since we're flipping the V1 and the V, we can remove the negative sign. And then from there, we'll divide across by R, so CV over R ln of T over T1 is going to be equal to ln V1 over V. And then for a natural log, we have T over T1 to the CV over R will be equal to V1 over V. And then using our ideal gas law, we can substitute in for our volume. So we have T over T1 is going to be equal to, to the CV over R is going to be equal to RT over P over RT over P. And these R's will cancel out. To clarify, T1, P1, T1, P1. So we're going to have, not T1, P1, T1, P1. In this case, it is R T1 over P1, and then these are just our unknown T and P. So we have T1 over T and then P1 over P. So now we can start multiplying by the reciprocal of this. So we're going to have T over T1. And since we're multiplying by the reciprocal, we have to add 1 to the exponent here. Is going to be equal to P1 over P. And we know that Cp equals Cv plus R at a given pressure and volume. So in this case, we can rewrite Cv over R Cv over R plus 1. We can rewrite that as Cv plus R over R, and then substitute Cp in. So in that case, we have T over T1 is going to be equal to raised to Cp over R is going to be equal to P1 over P. And from here we can multiply across by T1, so T will be equal to P1 over P. To clarify, before we multiply across by T1, we need to raise each side to the reciprocal power. So we're going to have R over Cp, and then we can multiply across by T1. And then from here, we can start substituting using our equation from above, right here. Right here. So let me go ahead and lasso that if I can find it. It might just be easier to rewrite it. So from here, when we substitute T into our equation, we're going to have dP over dz will be equal to negative mg r times T1. And then since we have this pressure here and this pressure here, we're going to end up with I believe P to the R over Cp minus 1. And then we have P1, and since it's we're dividing by a fraction, we're just going to end up with P1 R over Cp. And then from here, we can divide across by P to the R over Cp minus 1. Multiply across by the dz. So we'll end up with since we're dividing across by this, we're going to end up with 1 minus R over Cp. And then dP is going to be equal to negative mg over R T, sorry, that should be a T1 up here. T1 P over R Cp, or P1 to the R over Cp dz. And then we can integrate each side. So here we're going to be integrating from our known pressure to an unknown pressure. And over here, we're going to be integrating from our known z, our dummy variable of integration, z1 to z. And real quick before we integrate, I accidentally mixed these mixed up the order of our exponents here. So here we're going to have r over cp, and then down here we're going to have r over cp minus 1. So then when we integrate, we're going to add 1 divided by r over cp. So we're going to have, and since we're dividing by cp over r, I'll just multiply by, or dividing by r over cp, I'll just multiply by cp over r, and then p r over cp minus p1 r over cp. Gosh, you can tell I'm tired. It's going to be equal to this here is, and this is all constants. We can have negative mg over r t1 times p over r cp, and then we're going to have z minus z1. Again, this is our change in altitude. And then we can divide across by cp over r, and we're going to have p r over cp minus p1 r over cp. It's going to be equal to negative mg, and then we're dividing by cp over r, so these r's will cancel and we'll be just left with cp times t1. Forgot a 1 there in that pressure. P1 r over cp z minus z1. And then we can add this p1 over. So we have p r over cp is equal to negative m. I'll try that again. Negative mg cp t1 p1 r over cp z minus z1 plus p1 r over cp, and then we can factor out this p1 r over cp, and we'll be left with PR over CP is equal to P1 R over CP times negative, or sorry, yeah, so let's see, we have a positive 1 here, 1 minus mg cp t1 z minus z1. And then from here, all we have to do to solve for pressure is raise each side to the reciprocal of our power here. So we'll have P is going to be equal to, conveniently, we have the same power over here. So P is going to be equal to P1 times 1 minus mg over cp t1 z minus z1 raised to the cp over r. So here's our expression for pressure. And then to solve for temperature, we just have to use our equation from up above. Where is it? Right here, T, well, I'll just write it down here. Or, you know what, where'd it go? T is equal to, P1 over P to the R over CP times T1. We'll go ahead and drag that down here. So we just have to substitute this equation in for pressure, and you know what? Let me copy this so I can mark it without ruining our beautiful equation here. I'm going to have to use my keyboard. Well, this isn't working. I'll just write it again. And then I made a small mistake here. It's actually P over P1, not P1 over P. So we can substitute this expression in for P, and you'll notice that our exponents will conveniently cancel, and our P1 will conveniently cancel. So we're going to have T is equal to, it looks like 1 minus mg over cp T1 z minus z1 times T1.